Oh yeah. Yeah. Alrighty, it is 6 o'clock. Hello, everybody. Welcome to the March meeting of the Troy Astronomical Society. Thank you so much for coming. If there's anybody who's in Dr. Hudson's class, there's a sign-up sheet back there for your good extra credit. So we're going to start with some recent space news given by our Vice President, Ms. Veronica Lahue, and we're going to have a talk by Dr. Bankert on the Big Bang Theory and the beginning of the universe. As always, we plan to observe at every one of these meetings, but there's some clouds rolling in, and some of those clouds are going to have rain inside them, and both of those things are not things that telescopes like to interact with. So unfortunately, the observing is canceled for today, so we'll end the meeting as soon as we finish the Q&A after Dr. Bankert's talk. So without further ado, everybody, please give a hand for our Vice President.
Hi, everybody. I'm here to do the recent space news today. So I just want to start this off with a recent image from the Webb Space Telescope. So this very pretty image is Wolf-Rayet 124. Now, what you can see in this image are these clouds around the star. What's happening in this image is that the star has actually cast out its outer layers. This is a very big, bright, massive star. When stars this big get to the end of their life, they actually aren't as stable as they used to be. So instead of staying as a fixed shape and fixed volume, they actually just expand and contract over and over again until they explode and die. So sometimes this process can be very violent. So this star in particular, as it expanded, it actually blew out part of the outer shell of its star. So it creates this cloud of dust around it. Now, this dust is actually the main focus of this image, not just because it looks pretty, but because we can actually tell a lot of stuff about this dust. Astronomers can analyze this image and see how dense this dust is. And the main thing they're looking at is if this dust is thick enough to withstand the supernova that will happen. A supernova happens when a star of this age and this size can't hold up under its own gravity anymore, and it just collapses and explodes. And normally, this would blow everything out of the vicinity of the star. Everything would be gone. But thick enough gas could stay there, and it can turn into something like this. This is the Carina Nebula. And what's going on here is this is a star-forming region. There's so much cosmic dust in this area that it can condense down and create stars. The dust isn't just dust. It actually has every single element needed to create new planets and new stars. So if the dust in Wolf-Rayet 124 is thick enough to stay, it could create a new solar system. It could become a significant portion of a star-forming nebula. Now, the last thing I want to talk about here is the Webb Space Telescope is actually, it's an infrared telescope, but it has a whole bunch of instruments on it that can see different things. So the interesting here is not just infrared. Well, it is, but it's two different kinds of infrared. It's a composite image from two different instruments on the telescope, the near-infrared camera and the mid-infrared instrument. But they also released just the mirror image. And what you can see here, you can really see the knots around the star, these very big globs of dust. And that's the main thing that astronomers are looking at in this image to see if this star's dust could eventually create more stars. And that's all I have.
Does anybody have any questions for Ms. Vice President?
Yes, back there.
Do you know a secret about the gas giant that is about a six-sided shape?
Could you repeat that, please? I can't hear you. I'm sorry.
Okay, so here it is. It's called the big hexagon.
Oh, is that it? Yeah. the polar storm on Saturn. Remember that?
Oh, yes, yes, I actually did know that secret about that, about the storm on Saturn.
So it's called the hexagon.
Mhm.
But it's on Saturn, so it might be very hard to reach, and it's on the top of Saturn. But I'm asking you, how did those clouds form, and did somehow keep shape while also whilst changing color?
That's a fantastic
That
question.
is a great question for Dr. Robinson to
Oh, all right. So Saturn is completely composed of gas. There's no solid surface. You sound pretty smart, so I think you knew that, right? The polar storm is a collection of a bunch of different storms all interacting with one another. So there's a gigantic cyclone at the North Pole of Saturn. But because those winds are moving so quickly, because they pick up and shear a bunch of other gases around it, it creates 6 other mini vortices around the main vortex. So you have one gigantic spinning hurricane at the pole, and then you have one here, one here, one here, one here, one here, and they're all spinning in different directions. So it's kind of like when you look at an image of Jupiter, you see those bands, right? You see different colored bands that kind of like pinstripe it all the way down. Those are made of gas and clouds that are all at different elevations in Jupiter, and they're also moving in different directions. Anytime you have 2 gases at 2 different temperatures moving in different directions, basically makes the perfect environment for a storm, a cyclone, a tornado, a hurricane, whatnot. So the sides of the hexagon are caused by 2 different storms bumping up to each other, trying to push one, trying to push the other, and it flattens it out on one side. And then that same thing's happening over here, and that same thing's happening over here, and that same thing's happening over here. And so you turn it into what looks like a hexagon, but it's really 6 or 7 really, really powerful hurricanes all smashed up against each other. How'd I do? Is that good?
Yes.
Yeah.
Are there any other questions? Dr. Mike, did you have one?
Oh, yeah, I was gonna ask you, why, go back to your first image. Yeah. Why is there, like that big thunderstorm, why is it have all those big arms coming out of the sky?
There's actually an artifact from the way James Webb Space Telescope is manufactured. It comes from, those spikes aren't actually there, they're called diffraction spikes. They're from the arms that follow the mirror that takes the images. So they're not actually there. Any other questions?
All right. One more round of applause. And I transfer the powers of the talk over to Dr. Bankert.
Yes.
Spoilers.
All right. I want to make sure I was saying the right thing. Wanted to make sure I gave you the right lecture. I was just doing a real quick check to make sure we were the right one on. All right. Hello, everyone. My name is Dr. Justin Bankert. Right to that picture. All right. I'm going to be giving you a talk about the Big Bang today. So before I talk about the Big Bang, I want to motivate the Big Bang because, we have this theory, but why do we have the theory? All right, well, let's talk about this. So we start all the way back at like the fundamental beginning of cosmology. So when you have any kind of theory, you have to have these things called postulates. Postulates are assumptions that you have to make for the theory to work. You can't always prove, in fact, by their nature, you can't prove postulates within a theory. They're sort of like the bedrock upon which it's built. Think about saying like 6 plus 7 is 13. There's a postulate in that theory that you can add numbers and get other numbers. So you need these assumptions before you can go into the theory. Now, in cosmology, our big postulate is the cosmological principle. This one states that the universe should be the same in all directions and be the same no matter where you are. So this top one, same in all directions, is called isotropic, and the same everywhere is homogeneous. Now, if you lived in a universe that wasn't like that, then, you know, if you looked in one direction, you see a whole bunch of galaxies, looking in the other direction, you wouldn't see any galaxies, or very few. That would be not isotropic. Or, if, you know, we had this kind of universe, then two different observers would look out and see two totally different universes. This observer would see, you know, a universe that's much more densely packed with galaxies, and in their region, it actually almost looks isotropic. But this person over here would see very few galaxies around them, and, you know, be very directional. Now, we assume that our universe is like this. Now, can we actually truly prove it? Only out to what we can see. Beyond the observable universe, we have no idea. So we assume that the universe, beyond what we can see, is like the universe that we can see. And we have to make this assumption, because without this cosmological principle, we can't justify using the science that we do on Earth and extrapolating that to phenomenon we see out in the universe. All right, so with this bedrock assumption laid down, we can proceed. But again, it is an assumption that the universe works the way we think it does. If it doesn't, then we're just making everything up. All right, now while the universe is homogeneous and isotropic, it is not static. So a static universe would be one where everything stays the same. All the galaxies stay where they are, and, you know, time just unfolds. What we do know, however, is that the universe is expanding. So as time goes on, our universe gets bigger and bigger. With each passing moment, the universe is larger than it was before. Now, how do we know that? Well, we look at what are called spectra. Spectra are light patterns that we get from distant sources. And what we do,
Just draw it in the air like those old Disney Channel commercials,
right? Just appear. Does anybody even have access to or know where I might find a marker in this room with a whiteboard? All right, that's fine. I'll draw with a laser. All right. So imagine we have a light ray coming in, and we hit a prism. Prism looks like, you know, kind of a triangle. Think of the Pink Floyd album. As that light ray passes through the triangular prism, it gets separated out into its colors. You know, Roy G. Biv. Go across here: red, orange, yellow, green, indigo, blue, indigo, violet. Now, different elements, when they produce light, they have these fingerprint signatures in the spectrum. So this right here is the fingerprint of hydrogen. All these different lines are to do with hydrogen. And we can go to a laboratory, or we can look at nearby stars, and we can see where those lines are in the light. Now, when we look at a more distant object, like a galaxy that's far away, we see those same lines. This is the, you know, lines that make up that fingerprint of hydrogen. But what's different is that these lines are not in the same places as they are when we measure in the lab or when we look at nearby stars. They've been shifted towards the red end of the spectrum. And because of that, we call it redshift. Create a name as it is. Redshift is literally the shifting of these spectral features towards the red. Why, thank you.
You are a superstar.
Thank you. So, yeah. Got light incoming, and the prism breaks it up into that rainbow, and we can see these spectral signatures, these fingerprints that identify different elements. Now, the reason they get redshifted is because of a little thing called the Doppler shift. You guys are all familiar with the Doppler shift, even if you didn't know its name, right? You all have been in traffic or been on the road when an ambulance or a cop car goes blazing past you with its sirens, right? What does it sound like? Yeah. You guys know what I'm talking about. You got that high-pitched sound, and then there's this like transition into a low-pitched sound, like Dr. Robinson so aptly demonstrated for us. So what's happening is, as the emergency vehicle is traveling towards you, it's emitting sound waves. And each time it emits a sound wave, it gets closer to you. And emits another sound wave, and it gets closer to you, and emits another sound wave. So that causes all those waves to bunch up real close to each other. And so as they come towards you, they get artificially bumped up to a higher frequency. And then as it goes past you, now you're on this side, now every time it emits a sound wave, it's farther away from you than it was when it emitted the last sound wave. So it artificially stretches out those waves, causing it to go down in frequency. It's that high to low pitch. Now, it works, this is true of all waves, not just sound waves, but also light waves. Light waves also do the same thing. If you have a source that's moving with respect to us, if it's moving towards us, that light's going to go to a higher frequency or a lower wavelength. And so it'll be more blue. If it's moving away from us, it's getting, the wavelengths are getting moved farther and farther apart because each time it emits a pulse of light, it's farther away than when it emitted the last pulse of light. So it gets stretched out and gets redder. So this Doppler shift is what's causing these spectral lines to move towards the red. So look at this in another way. So here we have a star, and it emits some light towards us. So if the star is just static, it's just maintaining the same distance, we'll get that light at whatever natural frequency and wavelength it's emitting. If that starts moving towards us, though, the Doppler shift tells us that those waves are going to get bunched up, so we'll get this blue shift in the light. That'll be higher frequency, lower wavelength. If, however, it's moving away from us, every time it emits a pulse of wave, it's farther away than when it emitted the last one, so these wavelengths get stretched out. It's redshift. This is our spectral line, that we measure in the lab. A blue shift spectral line would be pushed towards the blue end of the spectrum. A red shifted line would be shifted towards the red end. So by looking at these spectral lines, which we get by pushing light through a prism, we can tell whether or not an object is moving towards us or away from us, just by looking at that spectrum. Blue shift, red shift. So when we do that, we look at all the objects out in the sky. For nearby stuff, it's sort of random. You're talking about like stars real close to us. This is us. There are stars all around us. Some of them are going to be moving towards us, some are moving away from us, some are moving sort of this way and that way. So when we look at stars, we see all sorts of different things. We see blue shifts, we see red shifts, all different degrees and magnitudes. But when we look at really far away things, so galaxies and nearby galaxies and farther away galaxies, even farther away galaxies, what we see is that the farther away we look, the more and more redshifted those galaxies become, which means that they're moving away from us faster and faster. This right here is a rather famous plot. Anybody know this plot? Hubble, right? This is Hubble's plot. So Hubble did the first data collection of this, and he was able to prove that the distances to some of these objects were much larger than the Milky Way. So Hubble was actually one to prove that there were things outside of our own galaxy. All right, so this correlation between distance and recessional speed, or how fast things are moving away from us, is called whose law? Hubble's law, yes. All right, so this effect is known as Hubble's law. The farther away we look in the universe, the faster stuff is moving away from us. Well, how does that work? Why is stuff farther away from us moving away from us faster? Well, that's because the universe is expanding. This is our proof that the universe is expanding. I told you before that we have proof, and that's the proof. The farther away we look, faster stuff is moving away from us. So to illustrate this, instead of a big three-dimensional universe that's kind of hard to hold in your head, let's talk about a one-dimensional example. Right? We've got paper clips on a rubber band. And each one of these paper clips is going to represent a galaxy. And these ants that are standing on the paper clips will represent observers in each of those galaxies. So we've got an observer over here in galaxy A and an observer over here in galaxy E. So as the ants ride on their paperclip galaxies, and we pull the rubber band farther and farther away, these paper clips get farther and farther apart. And not only do they get farther apart, but more distant paper clips recede at a faster speed than nearby paper clips. Now, I promised I wouldn't do any math, but I'm going to break that promise and do a little bit. Tiny, tiny, tiny bit. All right. let's say that we have 3 of these paper clips, and they each have a separation distance of d. Right? So we'll call this paperclip 1, that paperclip 2, that paperclip 3. Distance between paperclip 1 and 2 is d. Distance between paperclip 2 and 3 is d. Distance between paperclip 1 and 3 is, well, how far?
2D.
2d. All right, good. All right, so now our universe expands. Now, separation between 1 and 2 is 2d. Separation distance between 2 and 3 is 2d. What's the separation distance between 1 and 3? 4d. Right, 4d. All right, let's say this happened in some time, delta t. All right, how do we measure speed? Distance over time, all right? So our speed between galaxy 1 and galaxy 2 is 2d minus d over delta t, which gives us what?
D over delta t.
D over t. All right, what about the speed between 1 and 3? What? We have 4, that's how much it ends up being. We started with a distance of 2 over delta t. So what's the speed between galaxies 1 and 3? 2d over t. So the speed, if you're sitting on galaxy 1, you're watching galaxy 3 move away from you at twice the speed of galaxy 2. So the farther away the object is, the faster it's receding from it. And that just comes from the fact that it's all expanding at the same rate. Does that make sense? Before I move on, to make sure, does anybody have any questions about that? I know I promised not to do math, but I'll do just a tiny little bit right there. No more, I promise.
So is that implying that like the galaxies or stars that are at like equidistance from our reference frame would be moving at the same speed?
Yes.
So if they are equidistant, they're moving at the exact same
Yeah.
speed.
Yeah. And it's a measure of, it's like I said, it's isotropic, so it's the same in all directions, but a measure of how far away they are tells us how fast they're moving. In the back.
If you are using a rubber banded to connect them, why not just use a pulley system? It has the same gravitational force as a rubber band and can also hold things very, very thoroughly if you combine it with some rope.
Rope's kind of stretchy as rubber bands. That's why it's not as good for this example. We're using rubber band because it's stretchy. All right. So yeah, as we say here, if we're looking at the universe according to Ant A, their little paperclip galaxy, as they look, they see nearby galaxies receding, and then farther away galaxies receding at higher and higher rates. Now, this isn't just an effect of galaxy A's ant, but the same thing is seen near the ant in galaxy E. They see nearby galaxies receding, but more distant galaxies receding more quickly. The same reason as I described over there. This is happening to all observers in the universe, not just us. Because if it was just us, that would violate what?
Public law.
Not Hubble's law. Yeah, the cosmological principle, right? If things aren't the same everywhere, then we have no way of knowing how the universe works, because we can't go other places and can't go to galaxies far, far away, long, long ago. We cannot do that, so we have to assume that the universe works everywhere the same as it works here, or else, it's all make-believe. All right, so now let's take it from a 1D example to a 2D example. So let's imagine we have coins that we set on a rubber sheet, and we pull the sheet in all directions. Now, this rubber sheet is our universe, and these coins are our galaxies. As we pull the rubber sheet, the distances between all the coins increases at the same rate. So the coins are getting farther and farther apart, and more distant coins, so this coin to that coin, are getting farther apart at a faster rate. Yeah. So the important thing, though, here to understand is that the change in distance between these galaxies is not occurring because, don't think of it as like bits of debris in an explosion where there was some big push and all the things are like shooting away from each other. What's happening is that the coins are all still. They're all just sitting on the sheet. They're motionless, but the sheet is expanding around them. So the distances are growing because the sheet is expanding, not because the coins are moving. Does that make sense? There's no motion of the coins. The coins are just sitting on the sheet. The sheet's growing around them as you stretch it. So it's this expansion of the universe which is driving this recessional velocity, not any particular.
So not that it would be measurable, but this applies to everything that exists in the fabric of space-time, right?
Yes.
So is the distance between you and I increasing as we
No.
speak?
Is not.
We're in the same
All right.
galaxy.
The reason for that is because you and I are connected via the floor. If there was empty space between us, even our gravitational pull between small objects like you and me would be enough to overcome this.
Right.
It is a very, very weak effect. It only really affects things that are super duper far apart, like galaxies that really go far apart from each other. Gravity, out to a certain distance, gravity can keep these things from moving apart. The universe is still expanding around them. It's just that if they're close enough, the force of attraction holds them from getting too far apart from each other. And then when you're talking about like you and me in this room, there are much stronger things than gravity holding us together, like the electrostatic force, or the atoms in our body are being held together by strong, weak nuclear forces. So these things are way, way stronger than the expansion. Whatever is driving the expansion, which we honestly don't know, drives it. But whatever drives it is a very weak phenomenon. So it only really affects things that are not bound. So the question.
So with this theory, the universe is expanding, all the galaxies are moving further apart.
Yes.
Yet we have documentation that there's evidence that galaxies have collided.
Yeah.
How does this account for that?
Well, again, galaxies collide because they cluster. So just like with stars over here, we're not talking about the random motion of stars nearby each other. Galaxies cluster together.
Due to gravitational forces.
Yeah, due to gravitational forces. So these galaxy clusters are called bound objects. The expansion of the universe is not affecting these bound objects because gravity is holding them together. But there's enough distance between clusters of galaxies that the gravitational force between clusters is weak. So this is where the expansion is taking place between these clusters of galaxies because they're so far apart that the gravitational force between them is almost immeasurable.
So if they're so far apart, we can only observe so much. Is it like I'm sure it's not an unreasonable number of galaxy clusters that we can see, so that we can prove that we are moving apart, right? It's like,
oh my, yes.
Yeah.
So many galaxies that we can see.
Yeah.
just for reference,
Billions, billions, and billions.
what is our current the max distance that we're basically looking at? What are we currently looking
You
at?
can look out to a Z of 1,000.
Yeah.
Okay.
Look,
I mean, how far can we see supernova explosions? That's at least 15 million.
Well, 15 Z of 15.
Z 15.
That's 13 billion light years.
Yeah.
But I mean, honestly though, it's more accurate to say 15.
Yeah.
Those distances, light years.
Yeah.
Sorry, in cosmology, because the universe is expanding, we'll talk about a little bit. Distances, actually, it's the very next slide. Distances change with time. It's a nice segue into it. Distances change with time. So imagine we have two rulers. One of them is painted on our rubber sheet, and the other one is a solid ruler. As the rubber sheet expands, so here we have what's called a scale factor of 1. So the scale factor is the ratio of the units on our printed sheet versus our solid ruler. As time goes on, the rubber sheet expands and our ruler stays the same, so that scale factor increases with time. So the reason that I say it's hard to say, how far is the edge of the universe? You can't really say it in light years because as you go farther away, you're talking about going back in time. As you go back in time, the universe is what? Smaller, right? So as you look back in time, you're looking at a smaller universe. So the distances are actually different. The size of the universe is different when you're looking at a really far away object than it is today. So you can't really compare today distances with, yon era ago distances. Does that make sense? So when we say a z is a measure of redshift. So when we talk about really big distances in astronomy, we use redshift as a measure of, because redshift is a unit that it evolves with the universe. So redshift is something we just use to measure really large distances. When it's like a nature paper. You see it on a news outlet where scientists discovered a supernova 13 billion light years away. They say that because people don't know what you mean when you say redshift. But those supernova things are not actually 13 billion light years away. They're more like 30 billion light years away. Because if you were to take a tape measure and stick one in here and then run to them, right? That tape measure wouldn't say 13 billion years because the universe has gotten bigger since that supernova went off. It would start to say something like 30 or 40 billion years, light years. All right. Does that make sense? Because the universe is getting bigger, so the measurements themselves are changing with time. All right, so if we think of light waves as ripples in our little sheet, as we stretch that sheet out, the ripples also stretch with it. So imagine an electromagnetic wave emitted near the beginning of the universe. As it makes its way towards us, the space that it occupies is stretching. So as that space stretches, the scale factor changes, so the size of the waves themselves change. This is what's causing that redshift of the light. This redshifting of the light is happening because space is stretching and stretching out those photons. All right, now that we've talked about, we have our evidence. The universe is expanding. That expansion is ubiquitous, and farther away things are moving at faster rates than nearby things, which tells us that the expansion is ubiquitous. What does this mean? Well, if we see now that this has been going on for a long time. Look, farther things are moving farther away from us faster. Imagine the universe has been, on a home video, and we're, 13.5 billion years in the movie. We hit the rewind button. What is going to happen? What is the universe going to do? Yeah, we go backwards in time. The universe keeps going until what? I mean, if everything's expanding away from everything else, right? That's us. Everything's moving away from us. If we run back the clock in reverse, it looks like everything's coming towards us. Till eventually everything, all the things that are out there are on top of us. But everything everywhere is all at the same place. Yes. Yeah. Everything everywhere all at once, at the same place. It's a good movie. Won a lot of awards. We call that event, this co-location of all things, the Big Bang. Now, what is the Big Bang is a question that, if you look at joke things, people will say there be dragons. No. What is the Big Bang is a question that's, half in philosophy, half in string theory. Well, instead of telling you what is the Big Bang, I'm going to tell you what happens right after the Big Bang. Because, again, what is the Big Bang is half philosophy, half string theory. All right, but hopefully I've motivated for you guys that this is the evidence that we have for the universe, how the universe is moving. So you run back the clock, there must have been some point, according to most theories, or rebound theories, that state that there is no Big Bang. Most theories agree that there was a singular point for all matter and energy. All right, so now let's talk about the time right after the Big Bang, right after there be dragons. We've got our fundamental forces. Everybody here who's at least been my student knows this. We have strong force, electromagnetic force, weak force, and gravity. These are the 4 forces which shape our universe. All other forces that you experience are manifestations of these forces. Like, what's keeping me from falling into the ground? Drag. Normal force, drag us. The normal force. What is the normal force of manifestation? The electromagnetic force, right? There are electrons in the outer layers of the atoms of my shoes. There are electrons in the outer layers of the floor. Those two will repel each other and keep me from moving through the floor. So it allows me to hold this, push on this wall. Everything you touch and feel is a representation or a manifestation of the electromagnetic force. Now, what holds together our atoms, or the nuclei at least, the strong force. The weak force deals with radioactive decay. And then, what keeps us on Earth and keeps Earth around the sun? Gravity. All right, so these are our fundamental forces. Now, as we go to higher and higher energies, which if you think about a universe getting smaller and smaller, as you compress all that stuff together, it's getting to higher and higher energies because it's all squished together. As we go to higher and higher energies, these 4 forces start to meld into one force. So at fairly high temperatures, low in this scale, but high for us, the electromagnetic and weak forces combine to become the electroweak force. And the strong force, eventually, the high enough temperatures and pressures and energies, get the combination of these two. Anybody know what that's called when you combine all those together? That have guts. GUT, grand unified theory. So we put these together, grand unified theory. And then gravity, the sort of loner of the group, eventually, we believe, would combine then with those to form the theory of everything. So this one fundamental force from which all others sprang. Of course, this right here is the realm of dragons and string theory. We don't have a solid.
String theory is not the only game in town.
True. It's not the only game in town, but they're the ones who are most popular.
They're the loudest at the party.
Yes, they're the loudest at the party. The dragons left a while.
Yeah.
So up here is, I'm not going to talk about because, again, this is well beyond the level of a public talk. All right, but as time goes along, the universe expands and it cools. As the universe cools, this one fundamental force splits, gravity comes off first. A little bit later, the electroweak and strong forces come off, and then finally, the electromagnetic and weak forces split, and then we get to our present time, we have 4 fundamental forces. All right, now, something happened in the early universe. We believe. Again, all of this is highly theoretical. We can't go back to the Big Bang and push record on a video camera. So all of the stuff we're talking about here, we reconstructed from what we understand of physics based on the cosmological principle. We study physics here on Earth at Earth temperatures and in Earth laboratories, and we extrapolate that to other, the whole universe and energies beyond our imagination. All right, something happened between 10 to the minus 35 and 10 to the minus 30 seconds in the universe that we call the inflation of the universe. This inflation era is a superluminal expansion of the universe. What does superluminal mean? Anybody take a guess? Faster than the speed of light. Much, much faster than the speed of light. The universe went from being something like 10 to the minus 50 meters to something like 10 to the 9 meters in size in, this amount of time. That is so superluminal, it's incomprehensible. All right, why do we think this happened? If we have no way to go back and look at this. Well, when we look at the universe today, we see certain phenomena that don't make sense without an inflationary model or something to replace the inflationary model. There has to be something to explain these weirdnesses. The first one is called the horizon problem. All right, if I draw out the observable universe, this is us. This is how far we can see in any direction. When we look at stuff on this side of the universe, and we look at stuff on that side of the universe, something weird happens. it looks the same. Now, why would that be weird? Not directionality. How long does it take light to travel from the stuff on this side of the observable universe to us? Anybody? Well, if that's how far out we can see, then it's roughly, it took the age of the universe for that light to get to us. Now what about stuff traveling from the other side? How long did that take to get to us? About the age of the universe. All right, so that means that the distance between here and there is roughly what?
Twice.
Yeah, it's the speed of light times twice the age of the universe. Whoops. How can stuff be the same if it's farther apart than light can reach in one universe age? Well, that means that at some point in the really distant past, it must have been close enough together for light to be able to travel between them. And then something happened to push them outside of the reach of light traveling from one to the other. This would have to be a superluminal expansion. So this horizon problem says we see stuff on this side that's 13 billion light years away, and it looks like the stuff that we see in the other direction that's 13 billion light years away. That's weird. So, and this is the diagram I sort of drew up there. So CMB, we'll talk about a little bit later, is the cosmic microwave background. That's the most distant light that we can see. It's a couple hundred thousand. It's not quite the age of the universe. It's age of the universe minus about 300,000 years, but it's as far as we can see back. So if that light is traveling all the way to us for 13 billion years, and in the other direction for 13 billion years, and it looks the same, that's weird. All right, the other thing is the flatness problem. I am not going to go into this very deep. This is complicated, and I'm just going to mention it because it's one of the motivations. All right, when we look at our universe today, we look at the universe, the space that we observe the universe in is flat, is very, very flat. But there's no particular reason for it to be flat. It could be closed. A closed space is like, imagine you were, imagine you're on the surface of a sphere, like you were on the Earth. If I'm right here, and I go east, and I keep going east, and I just keep going east forever, well, where will I end up eventually? Right back here. That's what a closed space is. Expand that to 3 dimensions. A closed universe, if I just chose a direction, I went forever, eventually I get back to where I started. An open universe is the opposite, where things, as you get farther away, they're, the space itself, the opposite of closed. I'm not going to describe it. I'm not going to describe differential geometry. It's the opposite of closed. When we look at the universe, we see it to be flat. And there's no particular reason that it should be flat. I mean, the universe, when it came into being, could have been anything. So why? Because flat is the exact middle ground between open and closed. So it's perfectly between the two. Wow, how could the universe be so perfectly flat when it just as easily could have been very closed or very open or a little closed or a little open? Why flat? That's called the flatness problem. Don't have a good explanation except inflation. So these are our motivators for this superluminal expansion. All right, so how does it solve these problems? Well, inflation solves the horizon problem by saying that right after the Big Bang, everything is real close together. So here, imagine this middle dot is us, and particle A and particle B are 2 different, galaxies or something. They're on opposite sides of us. In the really early universe, everything is super close together, and so light is able to transmit back and forth between them. So everything can kind of come to an equilibrium. Then expansion happens. Boom. Universe expands out very, very quickly. Now A and B are way outside the reach of light for that age of the universe. Here's us, here's how far light can travel in the age of the universe, that dotted line. A and B are pushed superluminally, way, way, way outside of that. And then, 13 billion years later, they just start coming into view again because enough time has passed that light can travel that distance to us. So from a photon of light just emitted at the time of expansion reaches us 13 billion years later. So when we look at A and we look at B and we see that they're the same, how can that be possible? Well, it's possible only if at some distant time before inflation, they were close enough together to be able to communicate. All right, so inflation solves the horizon problem. It also solves the flatness problem. Because let's say before inflation, when the universe came into being, it wasn't flat. Maybe it was open, maybe it was closed, maybe it was really open or really closed, just a little bit open or a little bit closed. Either way, imagine your ant standing on a balloon that's got a radius of 10 centimeters. That's very close. You can do that exactly what I said. You walk forever, eventually you'll end up back on the other side of where you started from. Now, let's take that and expand it to a kilometer. It's still closed, but it's not very closed. Here it's very close. Here it's a little bit closed. But now expand out to the size of the universe. That is a very flat surface that ant is standing on. So superluminal expansion during the inflation epoch would take any curvature that existed and turn it to basically flatness. So inflation solves the flatness problem. So these are our two motivators for this expansion period, which it took us from a very small universe to a very big universe in an extremely short amount of time. All right, so now we're past inflation. I want to mention before going forward that this is our inflationary epoch. Right about here, where we got that separation between electroweak and strong. Right about here is also when we're going to have a separation out from normal matter of dark matter. Try to find a picture of it. They're not pictures you want to see. They are very sciencey. So about this time is also right after inflation, roughly when you got the separation of dark matter from regular matter. Right. So now we're past that. We're past inflation. Dark matter is separated out. Now let's talk about what's left over. All right. So in this period after inflation, the universe is filled with high amounts of energy. This energy is able to be created and destroyed through interactions with matter, so electrons, protons, neutrons, and antimatter, so positrons, antiprotons, and antineutrons. So when matter and antimatter come together, they annihilate. They produce high energy photons. And then those photons can combine to create new particles of matter and antimatter. So right after inflation, the universe is still extremely hot and extremely dense. Now it's cooled enough that you actually can have individual things like electrons and protons and stuff like that. Pre-inflation, everything was too dense for all the gluon plasma. After inflation, you can have, it's cool enough that you can have individual things like electrons and protons and neutrons. All right, but they're all annihilating each other continuously. Now, this keeps going until, for every creation, and the reason for this is so complicated, the guy who figured it out won a Nobel Prize. I'm not going to go into it. But for every 10 billion and one particles of matter that are created, only 10 billion antiparticles are created. So as this process of creation and destruction is going on and on and on and on and on, we're ending up with a tiny bit leftover matter. Until in the end, we use up all the antimatter, and we're left with is high energy photons and just this leftover sliver, 1 in 10 billion particles left of matter. So again, for every 10 billion antimatter particles, there's roughly 10 billion and 1 matter particles. So after all the annihilation is done, the universe is cooled down enough that these gamma rays can no longer spontaneously create new matter and antimatter. All we're left with is the matter. Antimatter is gone. Again, the reason for that is complicated. If you want to read it, I discovered why I won a Nobel Prize. All right. Next thing. Now we've got protons, neutrons, and electrons, all sort of whizzing around. Now, neutrons themselves are unstable. So neutrons will eventually decay into protons after about 15 minutes. So after about 15 minutes after the Big Bang, there are no more free neutrons. They've decayed, for the most part, all into protons. So after about 15 minutes, we're only left now with free protons, neutrons that are combined with protons, and free electrons. All right, now it's cooled down enough that we don't have matter antimatter annihilation, but it's still really hot and really dense. The entire universe is basically like the center of the sun, everywhere, all the time. So we've got these fusion events going on. This is the proton-proton chain. This is what happens in the sun. where hydrogens come together to form deuterium, which combine to make helium-3 and eventually helium-4. So I told you, after just a few minutes, all we've got left are basically protons and electrons. These protons start coming together to form helium. And they do that until the universe's temperatures and pressures die, because the universe is expanding. As as gas expands, what does it do? It cools down, right? The universe is expanding. It's filled with this superheated plasma, which is a charged gas. So it's cooling as it's expanding. So this fusion process can only go on for a few minutes, or eventually the temperatures become too low for that to be sustained. And as that happens, we end up with what's called primordial distributions of hydrogen and helium. So we start off with just protons. Protons are hydrogen, hydrogen are protons. And we fuse some of them to create enough helium and trace amounts of other stuff, lithium, beryllium, whatever, in the most tiny amounts of imaginable. All right, so that freezes out at about a temperature of 9 times 10 to the 9 Kelvin. So here we've got our protons and neutrons that are being created and destroyed. Then the neutrons, I said after a few minutes, the neutrons begin to decay away. There aren't really any neutrons left. No free neutrons left, and we end up with, this is our fusion epoch right here. So we end up with 74% hydrogen and 26% helium by mass. So that's our universe at this point. After a few minutes after the universe has been created, we've gone through all the stuff that I've been talking about. It's literally only taken a few minutes. All right, now we have a universe of extremely hot hydrogen and helium. It's so hot that it's still ionized, which means that these nuclei are not, they don't have any electrons around. They're not atoms, they're ions and electrons. Now, ions and electrons are real good at interacting with light. So those light rays, those high energy gamma rays that have been zipping around, they're cooling, they're redshifting. They're redshifting because the universe is expanding. So the universe expands, these things are redshifting. So they're going to lower and lower energies. They're still really energetic. They're just not energetic enough to create any matter. All right, so they're still interacting with all of these charged particles. And every time it interacts, it gets absorbed and re-emitted, absorbed and re-emitted. So there's no clear path for light through the universe, because it's like trying to look through like a really thick cloud, or really thick fog, which as people who live in Alabama, we are experienced with. You all know what I'm talking about. So here is water droplets that don't give the light a clear line of sight to travel through. Here is the highly charged particles, which are absorbing and re-emitting all of these charged particles. So for the first, so I told you we've gone through a couple of minutes. This is a couple 100,000 years now. All right, the universe is still expanding, still cooling. As it cools, eventually, it's low enough temperatures that when an electron sticks here, electrons and nuclei are sticking together all the time, but they're so hot that they just immediately break apart. Eventually, it gets cool enough that when the electrons stick to the nuclei, they stay there. Then we get atoms. And atoms, when they're nice and together with their electrons, they're a lot less able to interfere with this free flow of those photons. So at this point, the universe becomes transparent. So before this, you couldn't. There was, you say you try to look at something distant. There's no way. You literally couldn't see anywhere because the whole universe was opaque. After recombination, what this is called, we get a transparent universe that you're able to actually see through. Now, this last bit of light, the last light emitted from the interactions of these charged particles, is called the cosmic microwave background. And when we look out into the sky, we see it everywhere. This is a map of that cosmic microwave background. So you ask, how far out what's the farthest we can see in the universe? This is the farthest we can see in the universe. Why can't we see back past this? Exactly, because beyond this, the universe is opaque. This is a wall of fog that cannot be seen past. Right, of the sun. Yeah. This is a wall of fog we can't see past. This is the farthest you can see in the universe. All right, and then from that point, we're not really in early cosmology anymore. It's structure formation, stuff like that. So that's when I talk about the Big Bang.
Anybody have any questions for Dr. Bankert?
This might be very elementary, I guess, for you guys, but You were talking about how the universe expands and how the objects stay in the same place, but they would still move, obviously, because the universe expands.
Think of it like the paper clips on the rubber band. The paper clips
Yes.
themselves aren't moving, it's the rubber band stretching around them.
So my question is, someone brought up the fact that stars collide. How is that happening if everything is kind of moving?
Right, so stars and galaxies can still collide because they're in gravitationally bound structures. So the expansion happens between really distant stuff. So like the Milky Way and Andromeda are on a collision course. They're moving towards each other. Now they are able to do that because gravity is pulling them together, and gravity can overcome this expansion. Now the space between them, the space here, it's still growing, but gravity is pulling them together, even though the space is growing. So it's like if we were the difference. Here's the big. If I don't have a prop, but imagine Dr. Roberts and I are holding a rope. Hold the rope. All right. This rope is gravity. We pull on this rope, we can't get any farther apart. In fact, the rope's pulling us, sort of like contracting to pull us together. Now instead, let's imagine that we were holding a slinky. So hold a slinky. That's not how you hold a slinky. Let's hold a slinky. All right. Now, if we try to pull apart the slinky, right?
Yeah.
So when things are really far apart, the force of gravity is much weaker. So it's like a slinky. So they can still be moved apart. Whereas when they're much closer together, the force of gravity is a lot stronger. It's like us holding onto the rope. Just because the universe is expanding around us, that's us pulling against the rope. We're not going to get any farther apart. Does that make sense?
Yes, thank you.
How does this superluminal expansion with inflation sit well with relativity, like special relativity and the whole speed limit business?
Dr. Manning?
Yeah, so there's nothing moving faster than the speed of light. It is just space is expanding. There's no violation of it.
It was pretty close to what my question was gonna be. I was gonna ask, like, so if they were going so fast, how would they slow down? But it's just like expansion of space, so just the space stops expanding so fast. That would happen, like it just started to
Wrong, it
expand.
actually accelerates. So.
Well, and what, for the present day.
Oh yeah, it slowed down after. So inflation was that sort of like womp.
Yeah.
And then it sort of went into a more linear expansion. So there
So accelerate, then go to cruise control.
Yeah, it went, slow expansion and then womp and then slow expansion again.
Like, okay,
The question is, how? If you can answer that, there's a Nobel Prize waiting for you.
There's a nice, like, solid gold medallion that's
Yeah.
in the street and put around your neck.
And lots of money.
Any other questions?
All right, well, then everybody take some pizza so that we don't have anything to clean up. Otherwise, thank you everybody so much. We have our next meeting scheduled for the end of April, whatever the last Friday in April is. Dr. Michelle Wooten from the University of Alabama at Birmingham and the Starry Sky South Astronomy Club will be visiting us to give a talk on what they do and all of the outreach and events that they have. That's going to be at the end of April. And hopefully the weather will treat us a little better and we can actually observe. So stay tuned for the end of next month. And thank you everybody for coming.
Sorry about my
well out.